Yeah, good evening. In this session, I would like to demonstrate a small problem involving distribution of flow across pipes. In fact, though I am considering only two parallel pipelines, similar principles can be made use in order to identify the distribution of flow across a given pipeline network. A similar problem is already available in the fluid mechanics textbook by McCabe and Smith. May not be exactly the same type of data. So you can think of how to solve this kind of a problem analytically. The analytical solution may not be easy, but I may not be presenting that analytical solution during this demonstration, but you can also identify how you will be able to solve this kind of a problem using analytical methods. So 5 cubic feet per second of water at 10 bar and 25 degrees centigrade is being routed, to be routed through two different pipes. Pipe 1 has got a diameter of 4 inch and 20 feet length, whereas pipe 2 is having 2 inch diameter and 22 feet. So the input flow of 5 cubic feet per second of water, how much part of this should be sent through pipeline 1, and obviously the remaining will go into pipeline 2. Now, what kind of a logic or principle that we should make use in order to decide on an optimum distribution of flow? Maybe you can think in the background what should be the logic that we need to employ in order to identify a proper distribution of using these two parallel pipelines. Now let us try to solve this problem using Aspen simulation. Now as you can see, there is only one component that we are employing as far as this problem is concerned. So define that component, which is the first step. Go to the next input step, which is selection of a property model. As far as water or steam are concerned, you can think of using steam tables. So this is the best bet for identifying the necessary properties required for either steam or water. So go to the next step and choose simulation environment. You will be able to develop your flow sheet using this graphical user interface. So I have a splitter followed by pipes which are available under pressure changes. You can identify the difference between pipe and pipeline. So in this problem, I'll be using the pipe model. Followed by the second pipe. So one is larger in diameter, the other one is slightly smaller in diameter, but slightly longer in length. So let us try to connect streams. So this is the input flow, which is at a rate of 5 cubic feet per second. The exit from the first pipe. Similarly, we have to connect the flow to the second pipe. Okay. Now let us try to specify this problem. Once again, if you try to analyze this problem and try to draw a block across all the blocks involved in this problem, the only one input stream is S1. So we need to define this along with the blocks. So if you try to expand, so you are being asked to provide information with respect to S1, and in case of blocks, probably the splitter and these two pipes, some information we may have to provide. Given this information, it will be calculating the outputs. So let us go ahead to the next input screen. Now you are already given with this condition, water at 10 bar and 25 degrees centigrade. So let me add those details. And the flow rate is given in terms of volumetric flow rate, which is cubic feet per second. Given as 5. Right? So we were able to define three values. There is only one component, so thereby satisfying the degrees of freedom for a stream involving one component. So go to the next input screen. Now we are being asked to provide information with respect to the splitter. So we need to define how much portion of this input is to be routed through pipe 1 and how much should be routed through pipe 2. So for example, let us say we are dealing with the fraction that is to be routed through S2. So let me arbitrarily choose. So I would like to put up, let us say about 60% of the input flow is routed through pipe 2, and I am presuming S4 will be able to handle 40%. We don't know whether this is going to be optimum or not yet. This is only an initial estimate. So go to the next. Now it is asking information about the first pipe, which is named as B2. The pipe length, probably I should have changed the unit system to this. So pipe length of the first one is about 20 feet. Diameter is 4 inch. Right? So we have defined block 1, block 2. So the minimum information that is required. So go to the next input step. Now we are required to provide the information with respect to the second one. The pipe length of the second pipe is 22. Diameter is 2 inch. Did I convert that into inches? Yes. Right. You can see the required input is complete. So we should be able to run the problem and look at some results. So there were some warnings. Probably you can see that slightly later. I'll try to address this later. Let us look at the stream summary first. If you look at the mass flows or mole flows, so much LB per hour of mass flow is happening. Out of this, 60% is going into pipe 1 and the remaining is going into pipe 2. But this is not what is of our interest. We have assumed that what is happening to the pressure. Put it in the bars maybe. So this is the input pressure, right? And the exit from pipe 2, which is stream 3, is available at 9.4488. That means the pressure drop in pipe 1 happened to be about 0.56. What is happening to the pressure drop in pipe 2? So S3, S4 is the inlet stream and S5 is the outlet stream. So you can have a look at the inlet pressure is 10, but the outlet pressure is 0.043, almost 9.9 plus. That is the pressure drop in the second pipeline. So do you think whatever value that you have assumed here of sending 60% of the flow through pipe 1 and remaining 40% through pipe 2 is economical or is ideal or is optimum? So what should be the criteria that we need to employ in order to decide on this distribution? Probably you can analyze and you can see this thermal option is because of this problem, flash options. By default, it will be taking it as vapor liquid. And if you say liquid only, in both the cases, that option, that warning will be removed. Right. So you can just once again check it out. Now you can see that there are no warnings. The results will be the same. In fact, you can also look at the results of this block, stream results. So the input pressure is at 10 bar. Of course, input pressure is same for both the pipelines, but the output pressure is 9.44, a pressure drop of about 0.56. Whereas in the second case, the pressure drop is much higher. The pressure was at 10 bar, but the output pressure is at 0.043, more than 9 point something, right? 9.9 and so on. So how do we decide how much fraction should be routed through pipe 1 and how much fraction should be routed through pipe 2? So you can think of analyzing this problem. So the optimum distribution of flow should be in such a way that the exit pressures from both these pipelines must be similar. In other words, the pressure drop across each of the pipelines must be similar. Because the input pressure is similar, when the pressure drop is made similar in these two pipelines, the output pressure would be equal, right? So how are we going to handle this kind of a problem? So let us look at some kind of a tool which we have already seen, flow sheeting options, say new. what is the objective for us? We would like to, let us say, I would like to maintain the same pressure in S3 as well as S5. This is something similar to maintaining the same pressure drop in these two pipelines because the input pressure is same. So let me define P1 as the exit pressure from the pipe line 1. So this is a stream variable, and the variable you need to select stream variable. Stream is S3, that is the exit from pipe 1, and the variable is pressure. Okay. So I will also define another variable, say new P2, the exit pressure from the second pipe. This is also a stream variable. Stream is S5, the exit from pipe 2, and the variable is pressure. So we have defined two variables. Till now we have been looking at the maximum number of variables that you will be able to define happens to be only one, but I have defined two variables here. This is because I wanted to observe, I wanted to make these two values similar. So what I can do, try to do here is P1 minus P2. If I want to make them as equal, the difference must be made 0, right? So in other words, we are trying to force the condition that P1 must be equal to P2. Now this is the specification that I have given. Now what is the variable you are trying to manipulate or change? The split fraction. We have assumed initially this value as 0.6. Now I would like to play with this value such that the pressure drop in each of the pipelines is similar. So this is a variable associated with the block, which is the splitter, that is block 1. The variable is flow or fraction with respect to stream 2. That is the fraction that is being routed through pipe 1, whereas S4 represents the fraction that is going to pipe 2. So say this. Now let me consider this from 0.6 to maybe 0.9 or 0.95. So we have defined this design spec. We are trying to manipulate the split fraction and try to look at the exit pressures from each of these pipelines. And the solution that we are attempting in order to find out the optimum distribution is the pressure drops must be similar. So let me run this problem. Now as you have already seen, okay, let me go back to the main flow sheet. I will try to come back to this slightly later. So within 5 iterations, we were able to come to a convergent solution. What about the solution? So when we started with 0.6, so the pressure the pressure from the exit of the first pipe is 137 psia, whereas the pressure coming out from pipe 2 is only 0.62. But when this fraction is increased to about 0.866, the pressure from both the pipelines, the pressure from the exit of both the pipelines is made equal. So, you know, this is once again going to make use of secant method. This is the default method used by Aspen to solve any design specification problem, and you can just observe what is happening here. So what we are trying to do, remember, we are measuring the values of initially we started with an assumption of 60% of the flow should be routed through pipe 1. And having done this, solving this model, we will be able to know what is the pressure in this stream. Similarly, 40% is routed through this second pipe, and we are able to calculate after solving this model, we will be able to know the pressure that is at the exit of the second pipe. Now, this design spec, after knowing the values of P1 and P2, is checking up whether P1 minus P2 is equal to 0 or not. Otherwise, it is going back and adjusting the split fraction, which we started with a value of 0.6. So maybe within 5 or 6 iterations, we were able to come to a particular value of split fraction that is going to make the pressure from the exit of both the pipelines as equal, and this value is about 0.866. Now it is up to you to resolve whether you would like to consider this as an optimum distribution or not. Try to analyze in case if you are not convinced by my arguments, right? In the same way, of course, if you want, you would have defined delta P1, the pressure drop in pipe 1, delta P2, the pressure drop in pipe 2. But the moment you want to describe that as a pressure drop, it is not a stream variable. You will have to select that as a block variable because pressure drop is associated with the block pipe, and equate delta P1 to delta P2 like what you did with respect to P1 and P2. Whether it is delta P or P1 and P2, both are same because the argument's sake it is the same because the input pressures are same. So with this, I would like to conclude this session.